Hello everyone. Today we're going to walk you through a demonstration of SimToll, a platform for building toll booths on highways and bridges. SimToll was developed by 4 engineers at UC Berkeley, and today we'll be describing how this commercially valuable product can be used to improve the decision process in building toll booths. By 1, reducing traffic congestion, 2, anticipating and eliminating bottlenecks, and 3, predicting surges in traffic. We'll begin by going over the market to illustrate the current demand for roads and bridges and reducing congestion in traffic. The increasing activity in construction has led to a desire for installation for a toll booth in order to recycle the cost. As for the toll booth, our goal is to minimize the payment processing time. And next, we'll walk you through how our product, which is the revolutionary method to solve the congestion issue, is crafted to simulate any toll roads and bridges of any sort with a unique and handy interface. Last but certainly not the least, we'll introduce some of the new incoming features to continuously improve our already robust model. For example, we could create more add-ins to further strengthen all aspects of the product and even expand our product to other areas for other management purpose. As we discussed earlier, the key goal of our product is to become an essential tool to a decision process for contractors in their construction of the toll booth. With the algorithm in our product, we'll be able to predict the optimal number of toll booths after considering 2 types of payment methods, cash or electronic collection. Meanwhile, by simulating the daily peak traffic hours, SimToll will help the management company better prepare the number of working operators to reduce congestion in advance. Most importantly, since the initial capital investment is considered expensive to most of the contractors, our model will provide the best solution to eliminate any unnecessary expense and therefore maximize the return for the project.
After our in-depth market research, we have found a stable growing trend in the total mileage of toll roads in the United States. From the data that collected this past 10 years, it is obvious that both interstate and non-interstate toll roads are increasing, and at the same time, there is strong evidence that suggests the trend will continue in the foreseeable future. Let's look at the California transportation system. The state spending on highway is over 60% of the overall infrastructure spending. These favorable market conditions both indicate that the customer demand is tremendous in this space. The design of our product is not only limited to the complexity of the model. The user-friendly web application is implemented in Python and very intuitive to cater to people with different educational backgrounds. Our users will have control over a number of lanes for each payment method, driver arrival rate distribution, percentage of drivers with different payment method, and also the threshold waiting time for performance measure. So again, why SimToll? The seamless web integration in our product will provide our clients this analytics tool to achieve optimization both financially and operationally. Therefore, SimToll is considered the best fitting product for clients that need to work on any type of transportation project.
Imagine you want to create a toll road, or maybe you have an existing toll and want to analyze it. SimToll can be used for both of these situations. First, you have to think about the drivers. How do they pay? And do they carpool? These attributes define 4 types of drivers which are used in this model, which include a setup, enter, and leave event. During the setup, lines are created and you designate what line is which type. So let's say I want 3 lines of type 1, 2 of type 2, 1 of type 3, and 2 of type 4. Next, a driver enters with certain traits. Here, a type 2 driver entered. Then the driver chooses her line based on which is shorter. You control whether the driver only looks at lines of her type or if she looks at all the lines she can enter. Here, the driver did not carpool, so she wouldn't check any of the carpool lanes. Once a lane is chosen, the driver enters the line and pays the toll. After the driver pays the toll, she leaves the system. In the future, we plan to expand our product into tangent industries so it can model any similar complex system. We also plan to improve the algorithm so we can simulate parallel queues. In addition, we want to integrate our system with animations of the simulation, and this will help customers in understanding what our program does. Moving forward, we also want to work on building a dynamic simulation that can detect congestion and adjust accordingly. and we want to provide a more robust platform and enhanced user interface for our clients.
Here's the live demo of our product. Upon launching the web app, the user is confronted with a login screen. Here, different users can sign up and conduct their own simulation experiments. For this demonstration, we've created a test account for Professor Shubin. SimToll's dashboard allows users to customize several parameters to generate a host of scenarios. Users can select the number of lanes of each type. They can also specify the probability of drivers who pay electronically, as well as the proportion of carpool drivers. Another option is the ability to switch into lanes of different types. Alpha-beta values offer more flexibility and accuracy in representing ranges of probability distributions. Scalar multipliers are part of a formula for beta distributions, and for additional information, users can check out the documentation page to learn more about these parameters. Lastly, we define parameters for waiting time threshold, the longest acceptable time a customer has to wait. Beyond this threshold, we would consider these customers dissatisfied ones. And lastly, we have metrics to measure revenue and cost. When we're satisfied with our inputs, we can run the simulation. The following visualizations were produced using the default values. To identify bottlenecks in the process, we wanted our metric to be the percentage of customers who wait above a certain threshold. In the first chart, the proportion of electric paying customers who have to wait peaks at 44.2%. For cash customers, we see the peak at about 33.3%. However, one flaw of this metric is that it does not accurately account for dependencies such as peak hour. We then refined our model to aggregate time periods within intervals. Here, we see that in period 3, the proportion increases from about 20% to about 42%. This way, we can highlight anomalies such as peak period, an accident occurring, and more. This next graph shows us the length of interval or periods discussed earlier. For example, the first to second time interval consists of about 40 seconds. In this chart, we see that electric booths collect more revenue due to the speed of service. As such, one possible recommendation would be to convert more cash users to electric paying users. Finally, operation costs remain relatively constant throughout the duration of the simulation. That concludes our presentation. If you have any questions, feel free to email us at support@simtoll.com or call our toll-free line at 1-800-SIMTOLL. Once again, we'd like to thank you for listening, and we hope you enjoyed our presentation.